In the last unit, we used limits to calculate the exact slope of a curve. We also called this the instantaneous rate of change, and we also called this the derivative. However, that procedure was lengthy, so maybe there's a way we can develop some rules that will make finding the derivatives a little bit quicker. First, let's look at some graphs. So I'm going to start with the function f of x equals 2. All right, so here's the graph of f of x equals 2. And we want to know what the slope of this graph is. It's not too hard to look at it and realize there is no slope. If we were walking on this line, it would just be straight the whole way. We wouldn't be going up or down. If we wanted to, we can use our instantaneous rate of change to find the slope, but we could just look at it visually here. So if we have that the slope is 0, then that means that the derivative is 0. Let's look at the next one. We have f of x equals negative 3x plus 2. So let's graph that. So here is the sketch of this graph, and we want to find the slope. Well, since this takes the form of y equals mx plus b, we know the slope is going to be negative 3. But what does that mean graphically? What it means is I'm trying to find the slope at one point. The nice thing is that the slope at every single point is going to be negative 3. So let's graph that here on my second graph. The slope for every single point is going to be negative 3. The slopes of f of x is equal to its derivative. So the way we write derivative is f prime or f apostrophe of x. And in this case, it's going to be negative 3. So this is the derivative of f. All right, let's look at the next one. In this question, we're going to explore the slopes of the graph of one new function, and that's going to be g of x equals x squared. And I'm just going to draw a graph of that. Here is an approximate graph of g of x equals x squared. And what I'm trying to do is find the slope at each of these points. For example, let's say I want to find the slope at this exact point of x equals negative 2. At this point, I would need to find the limit of the difference quotient as h approaches 0. So this would be the limit as h approaches 0 of g of x plus h minus g of x all over h. This is what we did in the last chapter. To find the first one, I'm going to plug in x plus h into my function g of x equals x squared. And then I'm going to FOIL it all out. So I'm skipping a whole bunch of steps here to get x squared plus 2xh plus h squared. Then I want to subtract off g of x, which is just x squared all over h. X squareds go out, and then I can factor out the h. And then when I apply the limit, that second h goes, so I'm left with just 2x. This becomes the derivative. And the nice thing is that we can graph this. You'll notice that the scale has been calibrated to increment by 1 on the horizontal axis and 2 on the vertical axis. Let's look at this point here. At x equals negative 2, the slope is going to be negative 4. And let's see if that makes sense in conjunction with the derivative. If I look over here, we do have a negative slope, so that does seem to fit the bill. Okay, let's take some math notes. The first thing is a derivative is a function, f prime, that gives the slope of the curve f at any x value. And for right now, the way we calculate the derivative is by finding the limit of the difference quotient, or the instantaneous rate of change function, which is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, let's talk about notation. If we have a function y, the derivative is going to be y prime. Or if we have our function f of x, the derivative is going to be f prime of x. Then there's another notation. We can write dy, so the derivative of y over dx. So this means the derivative of y with respect to x. Or if our function is defined as f of x, we can call it df dx. Or there's a third way we could write it as ddx, and then we're going to multiply it by our function y. These three are called the Leibniz notation. All right, and then let's talk about what this graph actually means. So here I'll just put an arbitrary function. So here's point A, and what we're trying to do with the derivative is find the slope at that point. So the slope is going to be the derivative of the function at that point. This is also called the tangent line. And I think I have defined this in a previous video, but let's go ahead and add it here for completeness. We'll define the tangent line. This will be a line that touches the curve at one point and shares the slope of the curve. And in previous sections, we have found the equation for the tangent line, but let me go ahead and put it here. We're going to do y minus whatever the output value is for our point A. This is going to equal the slope, or the derivative at that point, times x minus whatever that point is. Okay, let's do an example. Example 1 says f of x is equal to 4x squared minus 5. F prime of x, or the derivative, using the definition of the derivative that we just talked about in the notes up here. So we don't have any rules as of yet. So to find the derivative, I already have f of x, which is this. So I need f of x plus h. This will be 4 times x plus h all squared minus 5. And to save time, I have already multiplied this all out. It is going to be 4x squared plus 8xh plus h squared all minus 5. Just a quick reminder, this is x plus h times x plus h. Now I could put all the pieces into the limit definition, so I get the limit as h approaches 0 of f of x plus h, so that's going to be all of this, 4x squared plus 8xh plus h squared minus 5, all minus f of x. So minus 4x squared minus 5 all over h. Now the negative distributes into 4x squared, so the 4x squareds go away. This negative also distributes into the minus 5, turns that into a positive 5, so the positive 5 and negative 5 go away. And I am left with the limit as h approaches 0. Now I'm going to factor out of h of everything that's left over, so h times 8x plus h all over h. Those divide out. Then when I apply the limit, this will go to 0. So I get 8x. this is going to be the derivative. Or I could also write it in a Leibniz notation with dy dx. Question B says to find f prime of negative 8 and explain what that means. Well, now I have the derivative function right here. So I just need to plug in the negative 8. So f prime of negative 8 is going to equal 8 times negative 8. This is negative 64. So this is going to be the slope of the tangent line at x equals negative 8 for the function f of x. So graphically, the function f of x looks like this, and it has very steep sides. So we're trying to find the slope right here at x equals negative 8. All right, in the next video, we're going to try and find a shortcut so we don't have to do as much work when we find the derivative. So see you then.